Well, before I start, this is the link where I have some examples for you to experience the quality or control of data by yourselves. And while you type it, I want to ask how many of you daily have to deal with curating data, pre-processing? Please raise your hands. Okay, so this talk is exactly about that. Yeah, this is, I think, a fact, but very clear. Cameron already mentioned there are no data which are not dirty. So at least let's ensure we can use it. So with all the range of data sets Cameron presented, you also went through all the legal aspects Christy mentioned. You decided, yes, this is my data set. I think I can use this. What to do next? Well, you need to make sure that data set is worth your time. So first of all, you want to make sure everything in the data set you need will be found. So there's a kind of a formal aspect of quality, resolution, behavioral information, events for functional MRI, a lot of stuff like that. Then there is more a quality aspect in the sense of, well, every experiment has a lot of sources of variability, and sometimes it's hard to control for all of them. So you need to make sure what is in the data. Finally, I will introduce some quantitative approaches to ensure the data are good, and some pre-processed data, how to control that for quality. And finally, if I have time, I will introduce some new cool thing we are introducing. So I'll start with the formal aspect of data. Cameron already introduced the bits, so that is great for me to jump directly into the bits validator. So the bits validator is an online tool for you to check that your dataset is bits valid. So here I'm uploading one dataset, and it says it has 133 files. The name of the dataset is DS005. And the first thing I will get from the bits validator is a summary with number of files, sessions, etc., tasks available, and then modalities in this dataset. And as we can see, this dataset is not valid. There is one error with the JSON file, and let's look into it. It's the dataset description. So every dataset has a description file, and this one is not compliant with the bits specification. We also have one warning. We will come back to this, but let's try another dataset. And in this time, the name is DS148. I have different files, subjects, etc., different tasks, and different modalities. And this time, the dataset is valid, and I only see two warnings. So first of all, the slice timing information is missing. So we know in this dataset, we will not be able to perform slice timing correction. So if you wanted to do that, this is not your dataset. And then this is a second warning about inhomogeneous files. So we can see files that don't have the same matrix size. Basically, there are two T1s with different sizes, which could be a problem for your processing pipeline. And then let's dig into the practical issues when you acquire. And everything stands not only for shared data, it also works for your data acquiring house. And I like to start with this phrase from Dali. Let's try to make the data as good as possible. So the most extended problem on all the data is head motion. The subjects usually tend to breathe and keep their lives during the experiment, and that translates into motion. They may relax and their neck gets closer to the padding, or they have to breathe a bit deeper at some point. From that to scratches, or maybe they move because they are asked to perform a task. And here in this slide, I show the typical aspect of heavily affected by motion dataset. This was meant to be a T1 weighted image, but basically it contains 3 ghosts of the same brain. Here we have another example, and some of the implications of head motion. Since whenever you introduce any object inside the bore of the scanner, you will modify the field. Head motion makes this perturbation of the field dynamic. It also affects your k-space and will introduce some spin history effects on your data. So I'm using, for this example I'm going to show now, I've used MRIQC, which is a tool for curating your data. This is the report for one T1 image. In this case, that is the subject ID. This is from the Abide dataset. And the first thing we can look at is this mosaic view, where we can see that this dataset has quite a bit of head motion. With this magnifier tool, we can see all those ripples in the frontal and the anterior part of the brain. Those are usually indicators of head motion. These ripples can be also GIFs artifacts, but that's a different source of the problem. Anyways, both issues will make your data challenging for pre-processing or useless sometimes. In the coronal view, you will also have a good sense of those ripples. I don't know if I think you can see them in the projector. And let's go to a second example. Again, the dataset doesn't look very well. Here, well, you see that there's some blurriness, but there are no clear ripples. So this time, when we find this kind of dataset where you can't really see very clearly if there are head motion ripples, you should go to the background and see what is there. So let's go there. And usually in the background, we see a lot of artifacts. Signal leaks to the background, and there you can see those ripples saying that this subject moved a little bit during acquisition. So in the background, we will see a lot of artifacts. So I always advocate to look at the background of the image and change the intensity levels to make these artifacts visible. And in the coronal view, again, we can see some of these ripples in the dorsal part. And finally, a last example. So again, I want to show in this example, you don't see the ripples very clearly. Well, in the white matter, you can see some, maybe not with the projector. Again, some ripples here. This side going that way. And sometimes we will find that, for example, this is in the coronal is more obvious. And this example was acquired on a Philips machine with Sense activated. And this kind of acceleration also has a noise reduction. So you will see a different pattern of noise in the background. Basically, it's almost removed. But if the subject moves, you can see how it tricked the Sense technology. So you can see those ghosts in the background. And everything was about in-plane or in-volume head motion. This is an example of an fMRI experiment where the subject was instructed to move, nodding. So in the beginning, there was I'm going to try to repeat it. So if you look at the beginning, basically the participant is nodding. And you can see the spin history effects in the beginning. If you look at those bands parallel to the acquisition plane, that's spin history effects. Okay, there you go. So to look at those spin history effects, we have this tool proposed by Jonathan Power, which is called the carpet plot or fMRI plot. And basically, it unrolls the 3D volume within the mask in columns. And each column is a new time point. And on top of it, we have plotted the frameways displacement, which is a measurement of how much the subject moved in this experiment. And you can see two thresholds, two lines. First, the blue line, solid line, is the average motion. For this subject, it was about 0.4 millimeters. And typically, we use a threshold of 0.20 millimeters to scrap out some of the time points if they moved a lot. And it's usually a generally accepted threshold. So if you look at the spikes in motion, they are usually coincident with a brightness, spatial brightness in the image, and then depth in this intensity. That's the basically spin history effects. So another way of looking at quality is some of the quality metrics we can measure from the dataset. So here we use the MRIQC to measure the frameways displacement in all the Abide-1 dataset. And the rightmost column shows that measure of FD_PERC, which is the percentage of time points that we would discard in this dataset because they are above the 0.2 millimeters threshold. And for Abide, this is a 16% of, the median is a 16% of time points. So it's quite a good amount of your data. For another dataset shared in OpenNeuro, it would go up to 24%. And we have a crowdsourcing tool called the MRIQC Web API, where all these metrics are uploaded when you run MRIQC. And on over 30,000 datasets, we see that at least 40% of the time points are dangerous to use because of extreme motion. There are other moving parts in the brain. For example, eyes, which usually leak signal through the face encoding axis. You can see a frontal to posterior encoding axis for the first image, left to right on the second. And then we also have blood flowing, so blood vessels may also generate some signal leakage. You can see it very well in the background enhanced view of any tool, but this is MRQC. And you can see this for this left to right face encoding axis image. This is another example. This is posterior to anterior encoding direction, and you can see how the sides of the brain are leaking some information. For example, in this case, this data may be useful because that leakage is not going over the brain, so probably your processing will be fine with this. More examples, low SNR, of course, inhomogeneity. For example, here in this image, in the middle of the brain, it's darker than the anterior part of the brain where maybe you can't discern between white matter and gray matter. And this is for fMRI. So this is an example without pre-scan normalization and with normalization. So this is without. And we can see how it's darker in the frontal. At some points, we don't have any signal. And then if you use the pre-scan normalization, it seems brighter. So you seem to have more signal there. However, if we look at the standard deviation map corresponding to the same data set, this is with pre-scan normalization, without, with and without, and once more. And this is the typical look of the standard deviation map of a fMRI scan. And here you can see how pre-scan normalization didn't raise the SNR of your image. So you have a lot of noise. More issues are N/2 ghosts, which happen because we acquire in Fourier space, and basically it's a cycle space, and when the axis doesn't have enough bandwidth, we will have replicates of the object coming in from both sides. Then other things may happen, like this is the DS30, the CNP dataset that Cameron mentioned. We found that there is a ghost. I don't know if you can see it there, but it seems like a ghost of the headset the participants were wearing is overlapping the gray matter. So this is probably going to break many of the free surfer runs of this dataset. And sometimes, well, anything can happen, and you can find all types of hardware failures, like here, or spikes. This is an element in the scanner which is acquiring energy, and at some point it releases it, and creates a lot of energy in one point of the key space, and those frequencies you see correspond to that point. This is another example contributed to us by Ben Inglis, and well, this is a data set where many spikes happen at many slices, and you can see these funny patterns. Finally, wraparound. So if you don't prescribe correctly the field of view of your data set, you will have the replica of the object coming into the opposite side of the axis. So in this case, you can see how almost the skull is almost overlapping the cortical gray matter in the anterior part of the brain. And an example of interaction of motion and also instability of the susceptibility inside the scanner are those bands in this data set. You can see how with time the distortion is different. And this problem, for example, would be very challenging and would indicate you that you should shim again before acquiring this fMRI in your protocol. Finally, I want to show you this example. So please look at this standard deviation map of an fMRI example. We had to change the reconstruction of these images, and we ended up with this standard deviation map. So I want you to try to spot the problem. I will show the problematic one again. And this is the good one. So yeah, you can see replicas of the eyes on those parts of inside those boxes. I'll show you more clearly here. So the top row is the old reconstruction algorithm with the eyes in those slices. And then the lower row is the good reconstruction algorithm without that big ghost from the eyes. So MRIQC is a tool that we propose to perform all this visual inspection of images. It also extracts a bunch of quality metrics, which are a vector of features of quality of the image that we are trying to use to build up a classifier that automatically tells you the quality of images. But at least for now, you can use it as a data curation tool. And we use those quality metrics to curate T1 images. And I wanted to also share with you those two resources, the MRIQC Web API, where we are collecting all these quality metrics building up a huge database. Right now we have over 40,000 images, quality metrics from functional MRI, and over 50,000 quality metrics from T1s. I'm going to skip this, and I want to show another tool that MRIQC provides you. So when you run all the subjects in your, you can go to mriqc.org. We have two very nice examples, one for Abide and one for the DS30 dataset. So I'm going to open up the group report and of the T1 images in the CNP, the DS30 dataset. And it basically collects all the quality metrics, which are all these different plots here for the whole database of DS30. And each point is a brain. So there are a bunch of quality metrics. For example, this is the CJB. Well, let's look into it. Click on it, and we see it's the coefficient of joint variation. And you can go to the definition, how it was computed. Maybe you want to know about a different quality metric, in this case the CNR, which is contrast to noise ratio. So all these metrics are used to try to understand the quality, and you can use this group plot to save time, because instead of going through all the images, which I recommend, you can try to figure out where are the outliers. So this was a good image, for example, and it looks pretty well. So I go through the report. I don't see anything significant. There are many other plots you can use to assess quality. And finally, we have this little widget here. I say it's good, and I just submitted it to the MRIQC web API. And this was a bad example, an outlier from the low part of a quality metric. And it looks pretty bad, very low SNR. So I can go all the way to the feedback tool and say, this is exclude case, very low SNR. I write it in the comments. You can't read it, but it says that. And it was submitted to the web API. So this way we are sharing all these expert ratings. That's a very nice way of getting information about how our data look. And we hope in the future, with your help, rating all your images, we will gather up a huge database we can work with machine learning. So this is another example for functional MRI, and this is one metric that goes to signal ratio. And I think I don't have anything else. Yes, I have. So let's look for some outliers here. Let's see, this is a metric related to blurriness. So the first image I will open should be blurry. And this is global correlation. So I'm also opening two examples that seem outliers. And this example doesn't look very bad. You have here all the tools I've shown you before. It has the inhomogeneity, but shouldn't be a big issue. Should be fine. Let's look at the bad case. This was the one with particularly high global correlation, and we can see in the carpet plot how there is a transition in the state of the scanner, and apparently there's a strong non-steady state in the beginning, and then it switches, and that's why it's dark. And here another example of high global correlation, which looked as an outlier. And again, we see a similar but inverted pattern. So please open your examples. I don't see too many laptops over there. But what I can do is I can open them myself and ask for volunteers. Okay, I don't know where's my, yeah, here. All right. So let's try to do this one.
Make the text bigger?
Yes, 1 second.
Which one is that?
This is from DS30. So you can get it online, by the way. So if you go to mraqc.org and, well, here, yeah, maybe this is not the best example because you get to the group report and then you don't know where is it. But you can click anywhere. And actually, this is the same. Okay. Yeah. So those are the two ways to get to this point. So one volunteer to diagnose this data set, please. I will help. And if you downloaded the package, there's a cheat sheet in the README file. So come on, one volunteer, please.
What do they have to exactly do?
Well, they have to tell me if they see any problem with this image. Wrap around. Yes. So maybe here in the screen you don't see it very well, but Fidel, our expert in quality, really, got to it very quickly. You normally see the wraparound very well on the background image, so you can see how the nose is here, and there was some wraparound in this case also in the frontal, So here you may have problems with your free surfer in this area over here. So since this is a wraparound problematic case, I'm going to report back to the MRIQC web API and say, well, wrap around. And, okay, there you go. So we have one more case labeled. Okay, next up, another example. I'm gonna make it easy. This is a bold functional MRI scan. So maybe too big. So everything looks good so far, but this is the standard deviation map for this case. So it seems like there was some kind of problem acquiring mostly all the slices in this scan. Although the carpet plot doesn't seem to be really bad. This is another cool part of MRIQC reports. It will give you, so if you ask for it, it will give you the principal components, the independent components, the composition of the image, and you can also spot problematic components. So this, for example, looks like a spike at this time point. All right, one more example, and one more example. We've done this. I don't know if this one is going to be easy here.
Can you say the ID so that we can find it right?
Sorry?
Just say the ID so that people can find it right.
Oh, yes, the ID is 11066. So, well, don't do quality control with a projector. It's a bad idea. So everything looks good. Okay, we got to the elephant in the room. Not that big here, but please focus on this. If you open it up in your screens, you will see at this axial view of the dataset, you will see a very weird pattern. So there was a hardware failure here, and this will totally confuse FreeSurfer or any other tool you use for structural analysis. I actually think you can also see in the background. So you see these little dots here. Those are like stripes. You would see them in the original image, and this was a funny problem I found. Let me see. Yeah, there's some wraparound, but we don't know if this is because of the headset, because of the, this is DS30, and it has this problem of the headset. Let me open one more. Okay. So this is the 01 stop signal 601. I don't know what is here. So this looks like a fairly normal multiband fMRI dataset with some motion. You can see the motion in the standard deviation maps. It usually looks like this, rings around the brain, which are where more changes you can see. And sorry. Oh, it doesn't. It's not very clear, but basically, this subject was acquired asking to move their head during blocks of 10 seconds. So this is a block where it was the person was moving the head, and you can see how the carpet plot. You can see it very well here, but in your computer you will see clearly changes between moving the head and not moving the head, and these are the different blocks. You can also see them in some of the components, like this, tracking the eyes, or this. Okay, let's do the last. Okay, so this is a very noisy one. Even with the projector, we can see inhomogeneity and illumination, very low SNR, and also there's some ghost here. Could be an over 2 ghost here. And I think, in the coronal view, in the sagittal view, it's more clear. Also in the background. So let's say exclude. And let's submit this to the Wave API. Very bad case. Yeah. So let's come back to the presentation. So basically you should dig into your data and try to catch all these habitual suspects, problematic issues. Let me talk a little bit about quantitative quality control. In MRQC, we have this pipeline, a very minimalistic pipeline to extract a set of features. So basically all the images undergo skull stripping, spatial normalization, very quickly, head mask calculation, also a hat mask to look for artifacts in the background. And from all those intermediate results, we extract all these quality metrics. We have a similar pipeline for functional MRI. We also perform some spatial normalization, averaging, and calculation of standard deviation maps and temporal SNR maps. We have a bunch of quality metrics that we inherited from the QAP of the pre-processed connectome project that Cameron introduced before. We like to classify them between some metrics after noise measurements, some that look into the information content of the image, some are just to detect specific artifacts, and then we have a miscellaneous box for blurriness and summary statistics, etc. Similarly, for functional MRI, we have some structural features, some more focused on temporal aspects like TSNR or global correlation, also artifacts, and a couple of quality metrics that we just used from AFNI. And the problem of quantitatively looking at quality, these quality vectors, is that there is a very strong relationship with the center of acquisition. So this table shows the Abide dataset. So each row is one subject that belongs to either one of the sites of the 17 sites where the Abide dataset was acquired. And each column is one quality metric, and we can see how they cluster very well together between sites. We first tried to site-wise normalize these quality metrics, and even though they fairly look a lot better, they don't seem as clustered around each site. Still, there are strong side effects in this data. So basically, we learned you cannot use the quality metrics directly. You need to elaborate a bit more if you want to really understand the quality of data sets. We tried to learn, and we did actually a classifier, a random forest classifier. This is the result of the importance of different features. We found that the QI2, which is one of those specific for artifacts in the background, was the most discriminant one, or the most important one. And we had to use a leave one side out cross-validation to make sure these side effects were not inflating our performance. Then just a quick comment about fMRI prep and curating the data, which has some data that have been processed. fMRI prep is a workflow to pre-process fMRI and also the corresponding anatomical information. It basically goes through these different stages where data on the left side we have the anatomical preprocessing, on the right hand side we have the functional preprocessing, and the data go through several steps trying to ameliorate the problems of quality we've seen before. So basically, for example, inhomogeneity correction or slice timing correction for the functional data. And one of these stages is, for example, susceptibility distortion correction, which basically makes our functional datasets look warped because of this artifact, this particular artifact. So if you have a bits dataset, then it's possible to check whether you have additional information to correct for this problem, or maybe use the field map less, what we call the field map less correction, which would be the last option. Everything is in the preprint we have online, so I'm not going to wait long here. And this is an example of how to use the report that fMRI prep generates to check the quality of your preprocessing. First, you have a brain mask and segmentation. Then you have an example of how the anatomical was co-registered to the template. Here, this is the functional part where we can see how susceptibility correction performed. You can look at the frontal lobe and see how it was more aligned with the anatomy. We can see some ROIs and also co-registration to the T1. Then you have another task for this same participant, and we can jump into the About section where we can see that this was processed with fMRI Prep 107 and the command. You don't see much, and no errors were reported. And finally, I want to introduce the MRIQC Web API. Basically, this is a service we set up to gather together all these quality metric vectors we were computing on every image you run through MRIQC. And basically, this is how it works. You run MRIQC on your laptop, and unless you opt out, the quality metrics and some anonymized metadata will be sent to a server where we are collecting all these metrics. Also, if you click on the feedback tool, your rating of the image will be also stored, and then you can query this API and make questions like the one I did about how many time points I will discard from any random data set. So yeah, wrapping up, the most important tip here is look at your data, and I wanted to show you this brain blinking to you because of susceptibility and homogeneity. So yeah, it's really blinking. And that's a ghost from the eyes. So then I also want to encourage you to share your data, but do so sharing your bad images, even though it may seem risky that you get a data set with a lot of crappy images. It's very good to learn from it. So if you have crappy images, don't worry, share them. If you identify them, please flag them. It will be very useful for others. Otherwise, in the future with MRIQC Web API, you will have the information. But yeah, share your data. And yeah, basically I wanted to show you from the most formal aspects of will this data set be useful for me? Does it have the metadata I need to, how to visually go through all the images? Thank you very much. This is the link we're sharing for this tutorial, and I can take some questions, I guess.
Yeah, we have time for one question. Thank you for this wonderful talk, first of all.